Okay, I want to show you the effect of dimensionality on superinsulating states from experimental point of view. This work was performed in big collaboration, and I will speak about superconductor and superinsulated states. This is two dual states. Both the states are non-dissipative. In superconductor states, we have zero resistance. In superinsulator, we have zero conductance. Transition between these two states usually observed in two materials. This is indium oxide and titanium nitride, or niobium titanium nitride. Is very similar material. Also, we have several systems where people observe insulating states, but they didn't show any superinsulating properties, and usually we speak about two transitions. This is superconductor insulated transition and superconductor metal insulated transition. Temperature dependence for our usual niobium titanium nitride films are shown on this picture, and we can speak about this superconductor to insulated transition with same interesting point of view. In system can be appear superconductor islands, and these islands placed into insulating matrix. Then in system we can find two energy, Josephson energy and Coulomb energy. When Josephson energy higher than Coulomb energy, we obtain superconducting states. When we have opposite situation, Josephson energy less than Coulomb energy, we obtain insulating state. And in this situation, at temperature less than 300 millikelvin, superinsulated state can form. Of course, we won't try this picture and making system with nanopattern. For example, his nanoperforated systems, his holes with distance around 100 nanometers between center of holes, and after such perforation, superconducting films transform to insulating films. Also, we can take insulating matrix and grow superconducting islands on this matrix, and here you can see temperature dependence of one island and temperature dependence of resistance for this system, and here you can see also appearing of superconductivity in islands. But nobody really show superinsulating state in this system. Why? Because usually we observe current voltage dependence like this. Here is current proportional voltage, small increasing of current, like to overheating, and nothing more. Why it's happened? As Christina shown in previous talk, in this system appear strings with very big size. For these samples, this size around 200 micrometers, but size of our systems only 100 micrometers, and insulating states cannot be established. How we can change this situation? One of them, we can go closer to superconductor insulator transition. Then temperature of BKT was smaller, and maybe it help us. Yes, it is help. Here's two current voltage characteristics for two really similar samples. This is one samples. Firstly was manufactured in 2016 years and measure these samples is closest to superconductor insulator transition, which of our samples. And you can see that here is something like threshold behavior with good jump from low current to high current, but after degradation at room condition, these samples goes far from superconductor insulated transition, and we cannot observe threshold behavior in this system. We should increase the length of our systems. Let's see on dependence these properties from length. For experimental, we use titanium nitride film, which is polycrystalline with size of crystallites around 10 nanometers. And here is temperature dependence of resistance. And let's firstly take mesostructure with scale parameters and place gold contact in different distance in these samples and measure different systems. We can measure between 1 and 6. This is 2.4 millimeters, or 2 and 3. This is 0.2 millimeters, and combination of this context. And now you can see that resistance between these contacts doesn't depend from length when temperature is high. But at low temperature, you see difference between these lengths, between these contacts, and then length of our samples is more than stronger our insulator. We observe similar picture when we work with system in magnetic field, and here you can see resistance versus inverse temperature in different magnetic field from 0.15 Tesla to 8 Tesla. And we describe this behavior with using BKT theory with finite electric screening length. And let's use same theory for describing our temperature dependence of resistance for system with different lengths. And here you can see sample with length 2.4 millimeters, and here a picture for all lengths. And you can see that screening length, effective screening length, is proportional to length of our samples. Really, it means that minimal size for our system, it is length of our size, our sample. Okay, if we will measure resistance for more resistive samples, here is average resistance, and here very high resistive samples. You see that also at highest temperatures there is no dependence of resistance from length. At low temperature we can observe any changes in resistance. Okay, let's go to current voltage characteristics for checking our assumption. And here you can see that at largest length we have very good jump from low current to high current with pure threshold voltage, but with decreasing of length, this threshold voltage disappear, and here we have smooth transition. Nevertheless, all of this threshold voltage are proportional to our length. That means that electric field in this system is very homogeneous. It's very unusual because length of our samples is very high, several millimeters, with macroscopic value, and usually we cannot observe homogeneous electric field in such scales. Okay, for samples with high resistance, we never observe pure threshold voltage. Nevertheless, dependence from length in this view, this jump voltage is again proportional to length. It means that at any resistance, at any disorder, we work with very homogeneous electric field. About this feature, Christina was talking previous presentation, and I will not repeat it. Okay, and in fact, we always work with insulating wires. But when we speak about superconducting wires, we speak about system wires very long, and this system, such system, have very small widths. For superinsulating wires, we have opposite situation. We can work with system which very wide, but this system should be very short. Okay, thank you for your attention.
Thank you. So, can you come to one of the first slides? You showed this STM measurements by Benjamin Sasepet before. At the beginning. Okay. So I understand that your measurement and also the theory is fully compatible with this picture in the system titanium nitride. Yeah. But what do you think? This is the so-called Bose superconductor insulating transition in the way now which was presented in this session. So, do you believe that there are other systems which go completely from superconducting to the insulating states via two-step transition? So first, due to strong electron interaction, they become just metals. Due to other mechanisms than what you presented. Do you think it's is there any possibility?
Really, it depends from properties of insulator in this system. I hope in next conference we show how properties of superinsulating states in non-trivial regime, and there we show difference between usual insulator and superinsulator. And if people who have transition into steps, for example, any silicide, molybdenum silicide, or tantal or something else, can repeat our measurements, then the states are similar. But if the insulator is usual insulator, then this two transition is really different transition.